Okay, very good. Great. Yeah, if you were here or if you were not here, then I pushed the code. This is not what I wanted to look at. This one here. So I put the code just on my GitHub, OpenFOAM coding, recurring short training. I put that in the chat as well. I think it's in the Discord as well. So you can just download the code from last week. And then I put a link as well, the recordings you can find. I put the Zoom link, but I also just put it on YouTube as well for last week's one. So the idea is whatever code I'm working on, I'll just push it to this Git so you can keep track and try out any stuff. You can follow along as well if you want. Okay, so if you want, you can download if you just go to this Git and go code SSH. If you want, you can uh, go somewhere and download this. So I'm going to use OpenFOAM 2412, but what I'm doing should generally work for most versions of OpenFOAM. But if you want to download this repository, you can go git clone and then just that address. And that will make a folder called OpenFOAM coding recurring short training. And it'll look something like that. Okay, I already have this. So I am in the folder here. So I just put it at this location. So the first thing I'm going to do, so the kind of plan for the 30 to 45 minutes today is I'm going to kind of build on what I did last week. So I'm going to take laplacianFoam, a basic kind of heat conduction solver essentially, or diffusion equation solver. I'm going to add a divergence or, sorry, a advection term to it. Just go through some details about the coding and how to add that, how to add the required fields for that. Then just play a little bit with the case, talk a little bit about some discretization schemes for advection and how they affect the solution. And then, assuming I have time, I will add a custom class. So I'll just show how to add a custom class for looking up a diffusivity field. And that would be a function of temperature, and just add that to the solver as well. So before I do that, I'm just going to tidy up the repository. So my test foam was our solver we made last week, and that was basically we changed laplacianFoam to solve a wave equation. So it probably makes more sense if I just rename that solver, let's say waveFoam. So it's solving just a wave equation. And then typically toolboxes for OpenFOAM follow the structure of OpenFOAM. So OpenFOAM, when you download it, it will have a folder called applications, and that's for all the executables. And then it will split those into solvers and utilities. So we created a solver. So a solver is something that solves some PDE, whereas utilities are pre and post processing executables. So I'll just follow that structure. So I'll put my waveFoam inside application solvers just to follow the OpenFOAM structure. And similarly, for test cases, OpenFOAM has this tutorials folder organized by physics, but also by solver. So I will just do it by solver at the moment. So I'll take my test case and I will put it inside tutorials waveFoam just to make things a bit tidier. Yeah, okay, great. So let me go inside applications, solvers, and I'm going to make a new solver. So I'm going to kind of do the same thing I did last week. So I'm going to start by copying, not tutorials, solvers, copy foam solvers, and remembering that foam, when you load OpenFOAM, you have all these environment variables. So if you go tab, you can see all of these, and these are just variables set to various locations in the OpenFOAM installation directory. So if I go foam solvers, this is the solvers directory. So they're broken down by physics. So I'll just go basic, and then I'll take laplacianFoam, and I'll just copy it to the current directory. So I now have laplacianFoam. I'm going to rename this. I'm going to add an advection term. So it's essentially going to become scalar transport. So it's going to be like another OpenFOAM solver, but I'll call it advection diffusion foam. Well, you can call it anything. So this is going to be our new solver, advection diffusion foam. I'll go inside that. I'm going to get rid of this over Laplacian by M. This was this other solver inside laplacianFoam. I get rid of that. I'm going to rename the C file to be advection diffusion foam.c. And then inside this make folder, which for the it tells the compiler what has to be compiled, I am going to open up that make files. And instead of telling it to compile laplacianFoam.c, it's going to compile advection diffusion foam.c. And then this is going to be the name of the executable. So I'm going to call it advection diffusion foam. And rather than putting in the Foam app bin, which is a location in the main OpenFOAM installation, I'll put it in Foam user app bin. So OpenFOAM also defines this location. This is important if you're compiling on like a server you don't have write access to, like supercomputers. So then you need to compile things into your own user directory, not into the main directory. Also, it's good practice. You don't want to accidentally overwrite anything. Okay, so this is just laplacianFoam. I've just renamed everything. So I will just go wmake and just check that compiles. So wmake is just the build system for OpenFOAM, as I had mentioned last week. So all it is doing is essentially it's just figuring out where the different files are, and then it's just pasting in this command here. So this is just a compiler command with a bunch of options, and it does two steps. First, it compiles the C files into what are called object files. They're like intermediate files, and then it does a second command where it links that object file with various other libraries into the final executable, and this is the actual location where it is. So if I were to type advection diffusion foam and tab, you can see it auto completes. If I try run that now, it'll start the solver. So it is just laplacianFoam. I just renamed it. Okay, so in another terminal, I am going to load OpenFOAM 2412 again. I'm going to make a tutorial. So I'll go to my tutorial folder and follow the same structure. Make there, what do they call it? Advection diffusion foam. And I will copy our test case from last week, my test case. So I'll put that here. So now we have our solver just here, our test case just here. Okay, so let's start making some changes. I'm gonna have 3 terminals. So I'll have one terminal for doing my compiling. This is just for convenience. So I'll do one that I'm gonna compile the solver in, and then one I'm gonna edit the code in, and then one where I'm gonna run the case. Okay, so here's our solver, and I'm going to update the application name, get rid of this groups. So Laplace, I'll just update the description, Laplace equation solver for scalar transport with an advection term added. So it only takes a second to add a short description. You might as well just make sure it's up to date. I'll add my author name as well, just in case someone else gets it, why not? As I have said last time, people tend to not write comments after the code works. So if you're not going to write the comments while you're writing the code, then just accept that you are not documenting your code. Okay, there's a few things I'm just going to get rid of, things we don't need. I'm not going to talk too much about these at the moment. We might come back to them in later sections. I'm just going to get rid of some extra options here just to make the solver a little bit easier to follow. Oh, sorry. I'm fighting with my keyboard. Okay. So at a high level, what laplacianFoam was doing, or now our advection diffusion foam, is it goes through this loop, which represents like a time loop, and then it constructs a diffusion equation. So it's a ddt, time derivative of a temperature field, minus this Laplacian of a diffusivity by temperature field. So there's no equal to 0 here, but it's implied that this thing is equal to 0. It's solving that equation. You could equivalently write this as this, and it will also work in output. So that's our diffusion equation. That's been solved, and then it's writing out some things. So let me go back into my create fields. Okay. Ooh. Okay, so some of these things I'm going to skip over, but most OpenFOAM solvers will always have this create time. It creates this time object and then this mesh object. We can find those later, but we won't look at them now. They're often the main OpenFOAM library, but there is this create fields directory. So if I ls here, you can see there is create fields. There's the solver, there's the create fields header file, and then there's a write header file. So if I go into that create fields, this is basically creating this T field object, this diffusivity field object, and it's doing some things like looking up properties or looking up the value for this diffusivity. I don't need this anymore, so I'm going to get rid of that. Okay, so what change am I going to make? Let me just check that still compiles. It's good to keep compiling. Don't write a bunch of code and then try to compile, because you're just going to get a bunch of errors. So it's better to write a bit of code and compile. Okay, so what do I want to do? I'm going to change this to equals because I prefer the equation looking like that. And then it's explicit where the equals is. So what I want to do is I want to add an advection term. So an advection term represents, in this case, it would represent that the heat equation we're solving is being solved on material that is flowing in some way. So if we're looking at heat transfer in some square domain, you can imagine that we're looking at a window and then there's material flowing through that domain at a certain velocity, and then we're solving for the temperature field on that domain. So you have a heat conduction effect, but then that's, let's say, battling against the fact that there's just a mass transfer moving everything in one particular direction. Uh, as you'll have seen, the characteristic of OpenFOAM is you have these differential operators, and the code is written in a way to make it look like the maths, to make it easier to construct the different equations or terms. So we want to add a term that looks like this. So we want to add that should be a plus, plus divergence of phi t. So we already have t, and then phi would represent like a mass flow rate. So in this case, it will be the normal component of velocity at all the control volume faces, or multiplied by the area vector. Okay, so if I try to compile this now, I'll get an error because it'll say it doesn't know what phi is. So the compiler says error use of undeclared identifier phi. So it doesn't know what phi is. So we need to create phi. So what is phi? So phi is a field defined on the mesh. And OpenFOAM convention is we will, in the solver, define the fields inside this create fields. So how will we do that? Without explaining what this IO object thing is here and this mesh thing is here, for now, if we just accept, if you want to make a field defined on the mesh, it needs to look like this. So it'll have something like vol scalar field, the name of the object, and then it has two arguments. So there's the first argument is this thing called an IO or input output object, and then the second argument called a mesh. I could probably spend half an hour on IO objects, and maybe that's a later session. But essentially, if you have some sort of data structure that you need to read from disk, as in read from your hard drive, essentially, some data, OpenFOAM uses IO objects for that. So without understanding the internal mechanics of this class, you'll see that it has a name. You broadly will recognize, you can see this runtime.time name, and you might see other things as well instead of time name. And you see this must read and auto write. So it's kind of talking about where to look for this information, what its name will be on the disk, and whether it's must read or read if present, or don't read it or write it, or etc. like that. So to create the phi object, phi is going to be a function of velocity. So the first thing we need to do is read in a velocity field. So in this case, we're actually going to assume the velocity field is prescribed. But you can imagine if you have an Navier-Stokes solver or something like that, you can actually solve for the velocity field. So U is the velocity field. It's not a scalar, it's going to be a vector quantity. So these vol fields, vol scalar, vol vector, vol tensor fields, a vol field is called a geometric field in OpenFOAM. So it essentially, it's an array of data, but it's associated with a computational mesh. So a vol field is essentially an array of values, one for every cell in your mesh, for every control volume in your mesh. It also stores information on the boundary. So if you have a vol scalar field, it's storing essentially a double precision float for every cell in the mesh, whereas a vol vector field is storing 3 double precision floats for every cell in the mesh. So that's our U, vol vector field. Its name is going to be U. It's going to look for that in the runtime.time name. So that's the time directory. So that will either be the 0 directory or 1 or 2 or 3 or whatever, some time directory. And it also needs to be associated with a mesh as well. So potentially in more complex solvers, you might have multiple meshes, like for conjugate heat transfer or fluid solid interaction, you might have a fluid mesh and a solid mesh or something like that. So we've only one mesh here, and we're going to say it's must read. And why not add an info statement as well? So we'll say reading field U. Okay, so let's check that works. I will comment that out. So in the spirit of incremental compilation, okay, that works. And then we will go back here. So we have our U field, and now we need to create our phi field. So phi is represents this volume flow rate in between the control volumes. So if a vol field is defined at all the cell centers, there's also a quantity called a surface field. So in this case, it'll be a surface scalar field. So surface scalar field is also a geometric field, but in this case, surface means it's defined at the control volume faces. So in finite volume methods, you often care about things at faces and things in the cells. So OpenFOAM also has something called a surface scalar field, and you can imagine you also have a surface vector field, surface tensor field, etc. So that's what phi is going to be. There are other geometric fields as well. There's also ones called point scalar fields. I think there's also edge scalar fields, and there might be area as well. There's a few other types that are less common. Point scalar fields is once again linked with the mesh, but it's one value for every vertex in your mesh. Edge is one for every edge in your mesh. Surface is one for every face in the mesh. Vol vector field is one for every cell in the mesh. So I will define this as area vectors. So in OpenFOAM, the face area vectors are called SF. And I'm going to take the dot product of that with the velocity vector. So that's what I'm going to define as this volume flux. So meters squared by meters per second, so meters cubed per second. A couple of things. Where is SF defined? Well, our mesh object has an SF function that will give us the area vectors. So these are the actual dimensioned area vectors. And then this U field, well, I can't, this ampersand represents a dot product. So I have a vector multiplied by a vector, an inner dot product, that will give us a scalar. But U is defined at the cell centers, but the area vectors are defined at the faces. So I can't multiply two geometric fields which are located at different points. So I need to interpolate the velocity field from the cell centers to the faces. So there's an operator in OpenFOAM called interpolate U. So that'll take a vol vector field and create the equivalent surface field. And then the interpolation scheme is defined in the case at runtime. So if I do that, I'm going to interpolate these velocity vector fields to get the velocities at the faces instead of the cell centers, and then get a dot product or inner product with the area vectors, and that gives us a volume flow rate at each face. So let me just check that works. Okay, that works. So actually, because this phi field appears so much, OpenFOAM actually has a built-in, I think it's called create phi header file. So what I did there, I could have actually just went include h because it gets used so much. OpenFOAM, any commonly used functions, they will just make header files for them. Okay, so now I have my phi field. I'm ready to go. So now I can compile this here. And it's okay. Okay, great. Now I have that. Okay, now I can go to the case. So this was the case from the last time. So I have this 0.orig backup of my 0 directory. So inside that, I have just a T field. If I run block mesh, what is this case? So this is essentially the cavity case. So it's just a cube or a square that looks like, doesn't look like anything at the moment. Okay, check my meshes here. Oh, what is going on? Great. I updated my ParaView today, which is always a good idea. So let me restore my old version of ParaView. Okay. So let's see if this works. The mesh is not showing, so it's something weird is happening with my ParaView. Okay, let me see what else are we doing here. Yeah, okay. So in this case, I basically have the cavity case while that's opening. So I have 100 cells by 100 cells. It's a 1 by 1. Well, actually, it's a 0.1 by 0.1 block. And we originally ran this as like a wave type problem. So we're solving for this T field. We set 0 on all the outsides, on all the boundaries. So I will wait for this 5.13 to open up very slowly. But while I'm doing that, I'll just make some changes to the case. So in the cavity test case, you have two boundaries, the top boundary, and then you have the three side boundaries. But I want to be able to specify the boundary conditions independently for the left, right, and bottom. So I'm just going to go into the block mesh and I'm going to edit this to have a left, which I think this is the left, a right, I think that's this face here, and bottom, which is the last one. So if I run block mesh on that, this power view is being incredibly slow. And then I will just update my boundary conditions here as well to match that. So I'll go left, and I will just set a 0 gradient condition, which is like an insulation adiabatic type condition. I'll do that for the other ones as well. Left, right, and bottom. Oh my god, this power view is taking forever. Okay, we finally have it open. Okay, we have a mesh. Good. Okay, great. Finally. So I will keep this power view open so we don't have to wait for that again. Okay, so if I look at the case, this is the initial case we have. We have a T field, and we're just setting the T field to be 0 everywhere. Okay, so let's set up some sort of interesting case to solve. So I'll set all the boundary conditions to this 0 gradient to begin with. And then as an interesting case to solve, I'm going to initialize to just have a region of hot material right in the center, and then I'll just solve it in time and see how that temperature diffuses. So to initialize that temperature field, I'm going to use this set fields dict, and I had this in the last case. So I just select a region of cells in the very center, and I set their temperature to 100 and then 0 everywhere else. So I will just make a backup of this 0 directory. The reason I'm doing that is after I run set fields, it's going to overwrite my T field. So if I go refresh, go back to 0, so you can see these are the hot cells and these are the cold cells around. Just for visualization, I'll slice that in the Z direction. You don't need to triangulate it. And then I will use, like last week, warp by scalar and warp it in the Z direction. Maybe like that a little bit higher. So I'm just setting the height of the surface based on the temperature, so we can kind of track more closely what's happening. Okay, so now if I try run my new solver, advection diffusion foam, the first thing you're going to see it complains about is it can't find the U field, and it's looking for that in the 0 directory. So that's our velocity, and you can see it's saying it's trying to read the velocity here. So that makes sense. So if I copy my P field to U, so I'll just make a new field by copying the old T field. And then I'll just update this to be a velocity field. So I'll change the name here. Instead of a scalar field, it'll be a vector field. It's dimensions. So OpenFOAM, the dimensions are kilograms, meters, second, temperature, and then whatever the other three that people don't use. So kilograms, meters, so it'll be meters per second is the dimensions. So this is the power, the exponent. So it's a vector, so I will set the initial value of the velocity field to be 0 everywhere, and then I'll leave 0 gradient for all the boundary conditions. So if I now try, I'll make a backup of that as well, just in case I need it later, and I accidentally delete it. So if I now run my solver, you'll see the next thing it's looking for in transport properties, it's looking for this DT file. So just to do these settings, I'll open up another terminal. So transport properties, if you remember last week, we actually had like the speed of sound and some other settings. So I'll set it to be 1e minus 3. I think this is an okay number. Let's see what happens. And then when I run it now, it's going to try do this interpolation for the flux, and it expects that to be defined in this system FE schemes. So I will go system FE schemes, and I need to just tell it how to do that calculation. So that will be here, and I will come back to this, but I'll set it to be this Gauss upwind interpolation scheme. But this is important, and I'll come back to that. And then it's this Laplacian scheme. It also wants to know how to calculate the Laplacian. So this Gauss linear is basically the only way to do it, and that's fine. And then the next thing, it's saying unknown asymmetric matrix PCG defined in system FE solution. So the OpenFOAM warnings can be a bit scary when you first see them, but normally it'll tell you exactly where to look for it. And if you just go look there, you can normally figure out how to fix it. So it's an FE solution. So FE scheme specifies the discretization, but FE solution specifies like the linear solver settings. So it's saying solving this T equation, it's defaulted this precondition conjugate gradient, but that's only suitable for symmetric matrices. But when we add this advection term, it becomes asymmetric, so you can't use that. So it's actually telling you here are the valid ones. So I'll use this big stab. This doesn't matter so much for now, but I'll just do it like that. And I think the preconditioner, I'll have to change it as well. Yeah, so I'll use this ILU method. Okay, we might actually get it to run now. Okay, super, it actually runs. I think we probably had too small a time step. So let's set a time step, maybe e to the minus 1, run to an end time of 1 second, so 1,000 time steps, and I'll get it to write out results every 10 milliseconds. All right, let me delete some of these things. And let's run the solver. Okay, so you can see it's running through each of the times and it's solving the equations, doing small number of iterations. So let's see what happens. So if you remember our velocity field at the moment, we've actually set to be, okay, that was pretty rapid. We've set our velocity field to be 0 at the moment. So that term is actually doing nothing. So what happened in the very first second, the diffusivity is so high, this value here, that basically the heat just spreads out everywhere. So maybe let's try a much lower term value. Let me get rid of this results and run it again. Okay, let's go back to that. Okay, so now you see what happens, that if you solve your diffusion equation in time, so this is just like heat conduction. Okay, so now it's a bit small, but you can see it's essentially this region of initially hot material that the heat is diffusing away. Okay, so probably I could find maybe 10 times bigger might be a good number to use in that case. Let's zoom things in the way. Okay, so the next thing I want to try is what happens if we turn on this velocity field to be a non-zero field. So if I run this now with a higher diffusivity, you can see like the thermal conductivity effectively. It's just spreading out. Okay, so let's open up this 0 directory where we define velocity. So we set the velocity is 0 everywhere. So how about we set it to be maybe 0.1, 0.1. So it's pointing from the bottom corner to that direction. So it's basically, imagine that we have the underlying material is moving at a rate of 0.1 meters per second in the x and y direction. So if we do that and rerun it, we will see what happens. So let me play it. Maybe the speed is too fast. Oh yeah, way too fast. So let me go much smaller than that. But effectively, you just see that the material is moving away. So it just moves over in that direction. So if I play it now, you can see it just starts to move in that direction. So you'll see as it's moving in that direction, it's diffusing as well. So maybe one interesting thing to try is, well, let's set the diffusivity to be 0. So let's basically set the conductivity to be 0. So that means the heat should only move because of this mass transport, this advection equation. So if we do that, what we would expect to happen, let's say analytically, is this square region should just rigidly move. But actually, when you solve this, you get a lot of smoothing, diffusion errors. And this is related to this upwind advection term. So let's see the effect of that. I'll just make it a little bit faster because it's not traveling very far. So if I go back to this FE schemes file, I set this div term here, this div phi t to be Gauss upwind. So Gauss upwind is a first order discretization, and it's known to be highly dissipative. That's not spelled correctly. Close enough. It tends to introduce a lot of smearing errors, and most of the time it's inappropriate. There's very few cases where using Gauss upwind is actually a good discretization. So by first order, I mean that as you half the mesh spacing, the mesh errors will also halve. So that's typically pretty poor. Second order is normally what you want to aim for. So there are some second order methods. So one is limited linear, which you have to specify a limited limiter value as well. So for example, if you try that one, let's see how that does. So if you do in this case, it's better. You'll still get smearing errors, but it's better. And as you refine the mesh, it will be closer to second order. None of these methods will, no standard methods will work perfectly on such a sharp discontinuity. So this is probably the worst case scenario for a scheme like this. But you can see you can get methods like that will work better. But there's loads of other ones as well. And if you want to try different methods out, in OpenFOAM, you often just do this banana trick. So if you just write the name of just write banana, then just see, it'll say banana is not a scheme. It's not known discretization. And then there are very many advection or divergence discretizations and described in the OpenFOAM documentation, but also in the literature as well. Common ones as well are linear upwind. So linear upwind is common for like Navier-Stokes. And that will be a second order upwind method. So you need the gradient of the field as well. So you normally have to write it like this to have the field. So that's second order. I think if I run this one, I think this is unbounded. So let me check. So if you run this, yeah, so you get something like that. So you can see you get unboundedness as well. You get these oscillations. But this is using the gradient scheme up here, so there's ways to bound the gradient as well. So I guess looking at the OpenFOAM tutorials is the best way to see what options are available. So I think if I run it like that, it will produce a bounded solution, I think. Yeah. Okay, so you get something a bit similar to limit to linear. So there's various reasons to use these different ones. Okay, let me keep going. So the next thing I want to do, and I'll see if I can do it in 10 minutes, is how about this diffusivity field? Rather than just being a constant, how about I want that to be a function of the temperature. So I could do that here, just calculate that field on the fly, but I want to introduce how to make a class in OpenFOAM, and I'll make a class for that just to give you an idea of how OpenFOAM is designed in terms of this kind of object-oriented class structure. So if I want to make a new class, the typical approach in OpenFOAM is you just find another similar class, copy it, and rename it. An alternative is there is actually a script called foam new. So if you write foam new source H, so this will make a new H file for you, and then you just give it a name. So if I say diffusivity law, so I'm going to make a new class called diffusivity law, and that's going to provide me with this diffusivity field. So if I do that and then C, all that did was it created two new files, diffusivity law.h and .c, and these ones here. So if I open those up, .h, this is basically just like an example of a generic class for OpenFOAM. And it adds in all the possible functionality you might need. And we can do, it builds the same for the C file. So the way it works in OpenFOAM and in C++, you make a H file, and that's where you declare the class. So it's like saying what the class looks like. And then the C file is where you define all the different functions. So that's where you actually say how the functionality works. So for example, if you have a function called add, you might say, declare it in the H file and say the function add will take two integers and return an integer. But you don't say how it actually does that. Whereas the C file will actually give the details of how it does that. So the reason you split it like that, even though you don't have to split it, you could just put everything in the H file. The reason you split it is you include the H file in, say, the solver wherever you use the function, and it's quick to compile. And then you can independently compile the C file, the actual details, and that can be independently compiled. It doesn't have to be repeatedly all compiled together. So it's just speed of compilation. Okay, so I'm just going to go through this and rip out everything that we don't need, and then check it compiles and then add the functionality we do need. Okay, so class, short description, custom class for calculating and returning a diffusivity field. Source files, I'm just going to have a C file, and then I will go author just to be consistent. So fair enough. See. Okay. I'm going to skip over a lot of the details here, but I will just keep the parts we need. So most of the stuff we don't need. All this stuff is just examples of how to use things. It's this class, we're not going to derive from anything, so it's just going to be a class called diffusivity law. It's going to store some stuff inside it. For now, we're not going to do it. OpenFOAM adds these no copy constructors. We'll just leave those. I'll skip that over that for now. We don't need any of this stuff. We'll have a constructor. For now, we'll just have a constructor that takes nothing. So I'll get rid of the other examples. I'll get rid of this selector stuff. And then we can have member functions as well. And these operators I'll get rid of as well. So I'm basically just getting rid of everything we're not going to use. So at the moment, the class basically has a constructor that takes nothing. So constructor is a function to define how to make an object of the class. And it has no functions and it stores nothing inside it. So it's not very useful, but let's just get it working first. And then this is the C file where it's defining the details of all the functions. So I'll get rid of most of this stuff. This is the constructor that does nothing. And here's our other constructors we're not going to use. We're not going to use the selector. Here's the destructor that does nothing. We'll have some member functions as well. So I'll get rid of that in a second and get rid of this. Actually, just to make it a little bit more interesting, I will add a member function and do nothing. So it will return nothing, and I'll just call the function test. It has a function inside it called test. And if I go back to the C file, I have to define the details of test. So I'll go test, which takes nothing. And okay, rather than do nothing, I'll just go hello world. Okay. So now this class is basically doing nothing, apart from it has a test function. Okay, so if I just go compile now, wmake, nothing happens. The wmake doesn't know that I want to compile those files. So I have to tell it inside make files that I want to compile the file. So normally what you do is you'll compile the C file. So I'll add the C file there. It will compile that file in addition to my solver, and then it'll make one final executable linking the two files together. So if I do that, it will compile it. It gives an error because in this C file it doesn't know what info is. So normally in the solver, we have this include fvcfd, and that just basically defines many commonly used functions in OpenFOAM. So you could add this here. This will include a load of things that makes it a little bit slower to compile. More efficiently is to find where info is defined and include just that header file. but include FCFD is fine for just kind of working. Okay, so that compiles. Our class does nothing, but at least it compiles. Now let's make an object of our class. So if I go diffusivity law h. So I have to include this at the top. This is just telling my solver what about this class. And then let's just make one of these. So before the temperature field, I'll just say diffusivity law. I'll call it if law, and doesn't take any arguments. And then it has a function dot test. So this line here will create an object of this diffusivity law, and then it will call the function inside it. So then if I go back here and run my solver, I'll just stop it and jump to the top. You'll see this hello world here. So okay, it did actually work. That's good. Okay, so what do I actually want from this diffusivity law? I want to be able to create a temperature field or a diffusivity field and then return it back as well and be able to calculate it as a function of, let's say, the temperature field here. So how do I do that? Well, I will store the field inside the class. So field vol scalar field, so one for every cell center. I'm going to have a diffusivity field called dt. So at the moment we already have this, it's in the create fields, but I'm going to store it here. And then also I'm going to have some scalar coefficients as well. So I'm going to assume that diffusivity is some function of the temperature. So I'm going to assume it's a linear function of the temperature. So I'm going to assume it's equal to so diffusivity, I'm going to assume that it's dt is equal to some coefficient a naught plus some other coefficient a1 by temperature. So these are going to be my coefficients. A naught, dimensioned scalar, and dimensioned scalar 1. So dimension scalars are just floats or doubles that also have dimensions for dimensional checking. So I have these three things defined, and then to create those, I need to have access to something. So to create a field, you need to have access to the mesh. So the constructor will need to have access to the mesh. I will skip over the details of this. I'm basically providing the access to the mesh for now, and yeah, that's fine for now. So that's just the H file. So if I go to the C file, this constructor now has access to a reference to the mesh. And then our three fields are here. dt, our three data members are data stored inside this class, dt, a naught, and a1. And we initialize them here. So we'll go dt. So this is giving their initial value when they're created. So I'll have a dt field. We'll have an a naught dimension scalar. And we'll have an a1 dimension scalar. So how do we create those? Well, if I just go back to my create fields, I can just copy the way it's done here. So I just need to do this. Back to the C file. So we're going to call it dt again, and we have to access time, but we only have access to the mesh here. You can get time through the mesh. I'll skip over that. We'll say it's must read, has to be read, and we can set the auto write. And then these coefficients will be, we'll set an initial value for them. So we'll set our dimensions. And their initial values. And let me see, I think that's pretty much everything we need just to store the information inside as a starting point. So let's check that compiles. Yeah, taking longer than I thought it'd take. So I might cut it short. Let me just get this working. Then I'll stop for this week. Okay, so then when I try to compile it, I'm getting an error that says it doesn't know what a vol scalar field is. So in this class here, I haven't told it about any other code. So I could include FV CFD again, but in this case, I know that it's looking for these vol fields. So I can just include vol fields. And I think that's probably all it needs. Okay, almost. And then it's complaining now in our solver, line 58, there's no constructor for a diffusivity law that takes no arguments. And that makes sense because now the constructor, I'm telling it, has to take a mesh. So if I go back here, so here when I created this, I have to pass a mesh object to it to actually construct it. Um, Great. So that will create the class. So at the moment, I can run the code, but it's basically not using my diffusivity law. It just creates it and it does nothing. So what I need to do to finish this, and will leave this for next week, is I want to add a function which calculates the diffusivity field as a function of temperature. So it updates it where I pass in the temperature field, and then we'll return it back to the solver. And then in the solver, I can use that new field to do it. Okay, I kind of went over now, so I will stop recording now and I can continue on with this next week.